Hi students! We left off on this slide doing the electron configurations, and we need to finish up the end of chapter 2 and move on to chapter 3. So just to remind you, we were talking about the number of electrons that each element has and where those electrons go. And we started with hydrogen and helium, and we saw that hydrogen has one electron, and the first place that it goes is into the first s orbital, the 1s. And then helium is atomic number 2, and that means it has 2 protons and 2 electrons. And those 2 electrons are both going to go into the 1s orbital. And remember that each orbital can hold up to 2 electrons. And then we took a look at lithium, beryllium, boron, and carbon. And we placed all of their electrons in the 1s orbital, and then we saw that after the 1s was full, we opened up the second shell. And the second shell has 2 subshells, the 2s and the 2p. And the 2s is like the 1s, it can hold 2 electrons. And then the 2p can hold 6 electrons because the p's come in threes. So when you open up the second shell, you get the 2s that can hold 2 electrons, and then the 2px, the 2py, and the 2pz that can all hold 2 electrons each. And when we got to carbon, we saw that when we have 2 electrons that are going into the 2p's, we have to distribute the electrons to the different orbitals before any of the electrons can pair in a single orbital, and that was Hund's rule. And then we did these examples: nitrogen, oxygen, neon, and sodium. And we said we'd come back to the next problems, which starts with number 5, magnesium. Now, magnesium is atomic number 12, right here. And that means that it has 12 protons and 12 electrons. So the first 2 electrons, so we have 12 electrons. The first 2 electrons are going to go where the first 2 electrons always go, into the 1s orbital. So we would say 1s2. And then after the 1s orbital, the next 2 electrons will go into which orbital? The 2s, that's right. So we have 1s2, 2s2, and we've used up 4 electrons out of our 12 electrons. So we have 8 electrons to go. And the next 6 electrons will go into the 2p's. And if we're wondering how do we know that, well, there's a few different ways we can look at it. The first one is on the energy diagram. We can see that we put 2 electrons in the 1s and then 2 electrons into the 2s, and then we start filling the 2p's, the 2x, the 2px, the 2py, and the 2pz. So we've used up 4 electrons, and then we have 5, 6, 7, and then 8, 9, 10. So we have 1s2, 2s2, and 2p6. And if we're looking at it with this chart right here, we can see that we go 1s, and then we come back down to the 2s, and we go 2p, and then we go 3s right there. So after the 2p6, after 6 electrons have filled the 2p's, we go to 3s. So back on this slide right here, we can write 2p6. Now remember, you could write 2px2, 2py2, and 2pz2, but it's just easier to write 2p6 there. Now we've used up 10 electrons and we have 12 to use up total. And we said back on this slide right here that after that we're going to go into the 3s. Now magnesium is right there, so that should indicate to you that magnesium is going to be 3s2. And indeed it is. The next orbital that we fill is the 3s. And if you add up all the electrons, 2, 2, 6, and 2, you'll see that that is a total of 12. So the electron configuration for magnesium is 1s2, 2s2, 2p6, 3s2. On to aluminum. So aluminum is right here. So there are 13 protons and 13 electrons. So that's one more than magnesium has. So there's 13 electrons here. So aluminum's going to have exactly the same electron configuration as magnesium, except we need to figure out what to do with one extra electron. Now, if we look back at the energy diagram right here, magnesium would fill up the 3s, so we had 3s2, and then we can see that the next lowest in energy is going to be those 3 p's there. So we have 3px, 3py, and 3pz. If we look at this chart, we can see that here we're going to hop on over to the 3p zone, and aluminum is right there. Now another way to look at it is with this handy dandy chart right here. So with this chart, what we can see is that we've listed in a column all of the s orbitals, 1s through 7s. And then in the next column, we've listed all of the p's. Now remember, you don't have any p's in the first shell. You have p's starting in the second shell, so that's why you see the p's starting there and not in the 1s. And then in the third column, we're going to list the d orbitals. Now the third shell has 3 subshells, 3s, 3p, and 3d. There are no d's in the first shell or the second shell. That's why you don't see them there. And then the f's won't show up until 4 and 5. Now with aluminum, we put the first 2 electrons in the 1s, and then we come back up here like this, and we come down and we can see that the next 2 electrons are going to go in the 2s. And then we're coming back up here and we can see that the next electrons are going to be put in the 2p subshell. Now remember, p's come in 3s, so when you have 2p, what you really have is 2px, 2py, and 2pz, each holding 2 electrons, so 2p can hold 6 electrons total. After the 2p's are filled, you're going to go to 3s. And then after 3s, you're going to come on up here and go back down to 3p. And we can see that right here. Okay, so that 13th electron for aluminum is going to go in 3p1. There we go. Okay, so the electron configuration for aluminum is 1s2, 2s2, 2p6, 3s2, 3p1. All right, sulfur. So sulfur is atomic number 16, so it has 16 protons and 16 electrons. And you guys can see that it's still in the p zone over here. So the electron configuration we know is going to end in p. Now, aluminum, we said, had 13 electrons and sulfur has 16 electrons, so we've got 3 more electrons than we did with aluminum. We've got 16 electrons here. So the electron configuration is going to be the same as aluminum and magnesium, except we've got to place some more electrons somewhere. So what we're going to do is put them in the 3p. So we've used up 2, 4, 6, and 12, and that means 16 minus 12 is 4. So we're going to have 4 electrons in the 3p. Okay? So if we look at this right here, we've got 3p1, 3p2, 3p3, 3p4 right there on sulfur. Okay, iron. Iron is in the transition metals. So we are right here at atomic number 26. So we've got 26 electrons to put somewhere. So let's just write for iron, we've got 26 electrons. Okay, so we're going to have 1s2, 2s2, 2p6, 3s2, 3p6, because we're going all the way here, and then we've got to go back down to here. Now there's a strange anomaly here, because after the 3p's are filled, when you're right here, when you have 3p6, you're going to go down over here and you're going to put 2 electrons in the 4s. So what we'll have next is 4s2 right there. Now, after 4s2, the next 10 electrons are going to go back into the third shell. Okay, so the 2 electrons in the 4s, they popped out and they put themselves in the 4th shell. The next 10 will go back into the 3rd shell, into the 3Ds, which have some crazy shapes. And you can see this on the energy diagram right there. If we fill up the 3p's, what we see is that the next lowest in energy is 4s, and then from 4s you go to 3d. So the 3ds are actually higher in energy than the 4s, even though the 3ds are inside the 4. Okay, so the 3d orbitals are closer to the nucleus, but those 2 electrons, they pop out into the 4s and go farther away from the nucleus first, because it's actually lower in energy. And again, the next 10 are going to pop into the 3ds. The other way we can visualize it is this. You see how we go 3d6 right here, and then 4s2, and then we come back into the 3ds. So the D's right here are shifted down 1 on the periodic table. We would think that they would be up where the 3s and the 3p are for the 3d, but it's not. They're shifted down. And if we look at the little handy-dandy cheat chart right here, we can see we will fill the 3p, and then we will go to 4s. So we're going to put 2 electrons in the 4s. And then you don't go to 4p, which would make sense, but you don't. You go back into the 3ds, and you have to fill that one first with 10 electrons before you put the next 6 electrons into the 4p. So if we look at the periodic table, what we'll see is we have right here 4s2, that's an s, and then we have 3d 1, 2, 3, 4, 5, and then 6. So 3d6 for iron. So that's 3d6. Now this looks kind of weird right here on the end because we have 4s2 listed before 3d6, but the electron configuration is telling you the order that the orbitals fill with electrons. So 4s2, even though it's outside of the 3rd shell, it fills before the 3Ds do. So that's why it's listed in that order. All right, tungsten. Tungsten is W, and it's way down here. It's atomic number 74. So we've got 74 protons, and we've got 74 electrons to place. So that's going to be quite a big electron configuration. So we have 74 electrons. So let's just go ahead and do what we've been doing. We've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then if we go from where we were with iron, iron was 3d10. And we can see tungsten's way down here. So we've got a whole lot more to go. So we're going to do, oh, I'm sorry. Iron was not 3d10. Iron was 3d6. Ah, my bad. Okay. So if we go on over to zinc, that will be 3d10. So iron is 3d6, cobalt's 3d7, nickel is 3d8. Copper is 3d9 and zinc is 3d10, and we're not to tungsten yet, so we can go ahead and put 3d10. And then if we're wondering, oh my goodness, what is after 3d10? Well, again, you guys can do it a couple different ways. The energy diagram, or this chart right here, and you can see that after 3d10 you're going to be in the 4p's, or you can use the little cheat sheet right here and see that once you've filled the 3Ds you go to 4p's. So all three of those things are going to tell you exactly the same information. It just depends on how your brain works regarding which one of them is going to be easiest for you guys to use. So back to tungsten right here, we're going to do 4p6, and 4p6 we've gone to krypton. Now we've got more to go, so we're going to go back down here, right here, and we're in the 5s there. You guys can see we are right here, 5s, okay? And how many electrons can go in an s orbital? 2, that's right. So we're going to do 5s2. Now the 5s is full, and we still haven't got to tungsten yet. So we keep going in order, and the cheat sheet will tell us that after 5s, we're going to go to the 4Ds, which you can see right here. We're going to the 4Ds. And how many electrons total can you put in the d orbitals there? There are 5 of them, and they each can hold 2 electrons. 10, that's right. Okay, so we go 40-10, and we're still not even there. So then we go to the 5p, and the p's can hold 6, so we go to 5p6. You guys can see that here, 4d10, 5p6. And we're still not at tungsten. So our 5p6 will be right here. And then we're going to come on down to the 6th row. So then we have a 6s2. And we're still not at tungsten. 6s2, we're right here. Now, another strange thing happens. What we do is after 6s2, we're going to do the 4f's. Now, notice how you have lanthanum And you have actinium right there. So that is giving you a clue that we're going into the lanthanide series. Also, if you look up here, you guys can see that we go atomic number 56, atomic number 57, which is down there, all the way through atomic number 71, and back up to atomic number 72 there. So those F's are actually located right there, but if we squish them in there, it would expand out the periodic table so far that we couldn't put it on a piece of paper. So we take the F's and we shift them down here. Okay, so all that blah, 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 what was I saying? I was saying what comes after 6s2? And what is after 6s2 is 4f. So I've written 6s2 here, and now we need to write 4f. Now the f's come in 7s, and each of those can hold how many electrons? 2. Each orbital can hold 2 electrons. So if you have 7 of them, they can hold how many total? 14. That's right. So we have 4f, 14 right there. And then if we go back to the periodic table, where we're at is right here, okay? So we've got 4f, 14, and then we have 5d1, because lanthanum is actually up here, okay? So lanthanum 5d1, and then we've got 5d2, 5d3, 5d4. So tungsten ends with 5d4. Now, again, the numbers can be out of order, like we want it to go 1, 2, 3, 4, 5, like that. But the order that electrons go into the different shells can be out of order. Like the 4 S's, those 2 electrons will pop out there before they'll go back into the 3Ds. So again, the electron configuration is just the order that the electrons fill the orbitals. So tungsten has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, and 5d4. Whoo, that was a really big one. So that brings us to the question, isn't there a shorter way to write this? And the answer is yes. And that is the noble gas abbreviation. So what the noble gas abbreviation is a shortcut. So what we're going to do is we're going to take the electron configuration from the previous noble gas, and then we're going to go ahead and write the rest of the electrons on the end. So if we have the electron configuration of carbon as 1s2, 2s2, 2p2, what we would do to write the noble gas abbreviation is we would go to the previous noble gas. Now remember, this whole column right here, those are your noble gases. And carbon's previous noble gas is helium. So we would write in brackets helium to indicate we have helium's electron configuration, which is only 1s2, and then we have 4 more electrons, and where are those? Those are in the 2s2 and the 2p. Now, if you're writing the noble gas abbreviation for carbon, it doesn't save you much time. But if you've got elements that have really large electron configurations, it can save you a lot of time. So let's go ahead and write the electron configuration for vanadium and bismuth. So vanadium has an atomic symbol of V. And if we find that on the periodic table, where are we going to be with that one? Well, what do you guys think? Where is it at? Number 23 up there. So we've got 23 protons and 23 electrons. So we'll write that right here. We've got 23 electrons. Again, that's because vanadium is atomic number 23. So vanadium's previous noble gas is back here at argon. So what we do is we say that vanadium's electron configuration is the electron configuration for argon, and we put that in brackets. And then we write all of the electrons that come after the electron configuration for argon. So we've taken care of all of these electrons right here. And this one ends at 3p6. So in order to get to vanadium, we'll say the electron configuration of argon, and then 4s2, and then 3d3. So 4s2, 3d3. So that saves you a little time. It saves you time, especially if you have something like bismuth. So bismuth, what we would do is we would find it at atomic number 83. So we've got 83 protons and 83 electrons. That's a lot of electrons. So what we would say is bismuth's electron configuration is this, and we'd look up its previous noble gas. So we have to go backwards this way and see that the previous noble gas is xenon. So my dog just yawned. So if you heard him, that's what that was. I'm sure you guys heard my cat earlier. Meow, meow, meow. She likes to talk. So yes, the previous noble gas is xenon. So we'd write xenon in brackets to say, okay, the electron configuration for xenon, and we've taken care of all of these electrons right here. And we can see that xenon ends at a p6. So we have 2p6 there, 3p6, 4p6, 5p6. So we're going to go here, and that means that we're going to be at 6s2. So we've got 6s2, and then we're not even to bismuth yet. And we're wondering what comes after 6s2, because once we get down into the periodic table a little bit, the electron configuration gets kind of funky. Now, again, we have lanthanum and we have actinium right here, and we're gonna go into the 4Fs before we go into the 5Ds. And how do I know that? Well, I would suggest you guys look at this chart right here. And especially this one right here that shows us that once we go to 6s, once we go through 6s right here, we're gonna go into 4f. And remember, the 4f's, they come in sevens. F's come in sevens. So you get 7 orbitals at a time. And each orbital can hold 2 electrons, so that's a total of 14 electrons. So we have 4F as in Frank, 14. And then once we go through the F's, then we're back up here. Oh, there's my dog yawning again. And we're gonna do 5D10. And once we do 5D10, we're right there. So we have 5D10, and then we're still not at bismuth. Ah! Okay, so after 5D10, what is next? So we see we go 5D, and then we go to the 6Ps. So right here, those are the 6Ps. So we have 6P1, 6P2, and 6P3. 6P3. Okay, you guys, we have a couple of slides left, but I'm going to end there because my dog wants me to let him outside, and I don't want you guys to have to listen to him whine for the next 10 minutes. So stay tuned for the next installment of Chapter 2, and we will get to Chapter 3. All right, bye, you guys.